Okay, so now let's look at the Hessian, okay? So we can, instead of viewing this linear connection, nabla, as a map from the tangent bundle cross the vector bundle to the vector bundle, okay, which takes x comma t and sends it to nabla xt, we can actually view nabla as a map from the smooth sections of the in the case, let's just fixate on the not any arbitrary vector bundle, but just the tensor bundles in this case. We're fixating on the tensor bundles. Then we can view nabla as a map from the smooth sections of the RS tensor bundle to the smooth sections of the cotangent bundle tensored with the RS tensor bundle. Okay, so that gives us basically nabla is a map from gamma infinity of tensor RS TM to nabla infinity of tensor RS plus 1 TM. Okay. Okay. So why is this the case? Well, if we remember, we're adding a copy. Now we're just saying, okay, nabla, instead of viewing it as a map from a larger domain, we're just going to add that information to the codomain, okay, by saying, okay, if the output of this nabla, okay, so nabla takes in an RS tensor T, gives me an RS plus 1 tensor nabla T, where the final input, the S plus 1, the final input, right, is going to take in an S plus 1 vector field X, and it's going to return an RS tensor nabla X of T. Okay, so let me just show you that. Okay, so you can pause the video. Okay, so we have this nabla map, nabla T, which now is an RS plus 1 tensor field, and the final component is the final, if you input all of these components, the final input vector field X will just result in taking nabla X of T and evaluating it on the RS components, okay? So with this definition, we can iterate nabla to get nabla squared, okay? We can iterate nabla to get nabla squared, okay? And you can solve for this formula, okay? So essentially, nabla squared T of X comma Y, well, okay, first we're going to evaluate on the final component. We get nabla Y of this RS plus 1 tensor nabla T, this RS plus 1 tensor nabla T, okay? And so now we have to use the formula, remember this, we have to use this formula for this induced, for the covariant derivative of a tensor field, namely, we take the covariant derivative of the tensor field evaluated on its components, and then we subtract the sum of the tensor field evaluated on the covariant derivatives of the components, okay? So use this formula, and we essentially first take nabla Y of this nabla T evaluated on its component, so that's this expression, nabla Y, nabla xt, minus nabla T evaluated on the covariant derivative of the component. So that's nabla T of ... comma nabla Yx, which is just, by definition, nabla in the direction nabla Yx of T. Okay, so I wrote this out, I believe, here. Yeah, so you can see, yeah, this is what I wrote out to kind of explain this, and I just explained it in words, but you can pause the video and understand what I'm saying for this equation 8 here, okay? And then if you consider just a 0, 0 tensor, so a smooth function, then what we're going to get is the Hessian, okay? So if you consider a 0, 0 tensor a smooth function, then I did the computation up here, get this nabla squared is nabla Y of nabla F of X, okay? So first we are going to take nabla Y of this basically evaluated at its component. So this is just nabla Y of nabla X F, and then we subtract nabla F evaluated on nabla Yx right here. And so this just gives us Yx F minus nabla y xf, okay? All right, so this gives us the Hessian of a function, okay? So the Hessian of a function, nabla squared f, is equal to, nabla squared f is a 0, 2 tensor, and when we evaluate this on vector fields x, y, we get that nabla squared f of x, y is equal to yxf minus nabla yx of f, okay? And the point is that we can ask the question, when is this Hessian symmetric? When is this Hessian symmetric? And so if we take nabla squared f of x, y minus nabla squared f of y, x, we get precisely the torsion tensor applied to the function f, okay? So this torsion tensor is basically, when you evaluate it on x, y, it is nabla xy minus nabla yx minus the commutator of x and y, okay? And so this torsion tensor precisely measures the failure of the Hessian to be symmetric, okay? And notice that the torsion tensor, it is a true tensor because it's C infinity m linear in both arguments. So t of fxy is equal to t of x fy is equal to f of t of xy, okay? All right, so we have this torsion tensor, okay? And the torsion kind of measures, in a sense, how a vector field twists when you parallel transport in a direction. So if you parallel transport like along, if you think about like R3, actually just take a moment, pause this example. This example gives a nice kind of intuition behind the torsion tensor, okay? So point is, torsion kind of measures how much a vector twists as you parallel transport it along a line, okay? And the point is that that we want the Hessian to be symmetric to generalize the notion of partial derivatives commute. So we set the torsion to be 0, okay? And this, we require that the connection is torsion free, okay? And then if you do a local computation, okay, so local computation, first of all, you can view the torsion as a 1-2 tensor, okay, where the first input is a covector field that just evaluates omega of t of xy, okay? So then the torsion can be thought of as a 1-2 tensor in this following way, okay? And so, let's just, yeah, this is the definition of the torsion tensor right here, okay? And so then, when we evaluate this in components, okay, if we look at the components of the torsion tensor, we use local coordinates, okay, local coordinates. And then now, to set the torsion equal to 0, we can perform this calculation. Notice that the partial derivatives always commute in Rn. The point is, partial derivatives commute in Rn, so this will vanish when we evaluate this. So we're going to get these, we're going to get, since by definition of this, of the Christoffel symbols in coordinates, we have that basically we can write the torsion tensor evaluated on partial a comma partial j in terms of the Christoffel symbols, and then solve for this component t superscript k subscript ij, and it's just the difference of the Christoffel symbols lambda k subscript ij minus lambda k subscript ji. Okay, so basically, in coordinates, we recognize that we need the Christoffel symbols to commute in the bottom two indices to make the connection torsion-free. Okay, so that's this corollary, is that nabla is torsion-free if and only if the Christoffel symbols commute in the bottom two indices. Okay, all right. Now, the final thing that we want to require is this metric compatibility. So the metric compatibility is essentially saying, okay, we want the linear connection to be metric compatible in the sense that each parallel transport map actually preserves the inner product structure, okay? So we have a bunch of parallel transport maps which are governed by the linear connection or determine the linear connection, vice versa. These parallel transports maps P gamma from 0 to t, which basically sends the tangent space at gamma of 0 to the tangent space gamma of t. If we include the fact that these tangent spaces actually have an inner product structure, then this tangent space at gamma of 0 has an inner product structure given by g evaluated at gamma of 0. Similarly, the tangent space at gamma of t has an inner product structure given by g evaluated at gamma of t. We require that this parallel transport map is an isometry between inner product spaces. So it preserves the inner product. Okay? And then when you require this conceptual notion, okay, that parallel transport essentially preserves the angles between two vectors, that is what's called metric compatibility. And you can take a look at this proposition and you can find that, okay, there's an equivalent characterization which basically says, okay, we're going to require that the metric is parallel. So nabla x of g is equal to 0 for all vector fields. So the covariant derivative of the metric is identically equal to 0. And then you can solve for this equation setting g to be parallel in terms of basically you just unpack the formula for the covariant derivative, and this will tell you this metric compatibility condition, which is the most commonly taught condition, which is essentially a product rule. Okay, so x of inner product yz is equal to the inner product of nabla x y comma z plus the inner product of y comma nabla x z. Okay. So now when we come back, we're going to talk about, okay, so I should just quickly mention, if you have a linear connection on a Riemannian manifold which is torsion-free and compatible with the metric, then this is called a Levi-Civita connection, and it is unique. There is a unique way to solve for the Levi-Civita connection and express it explicitly in terms of the metric, and this is actually the fundamental theorem of Riemannian geometry, which states that on any Riemannian manifold there is a unique Levi-Civita connection, which can be constructed, the Christoffel symbols for that connection can be constructed in coordinates explicitly in terms of the metric, and we're going to discuss that in the next video.